Hello and welcome back. Today we turn our attention to complex sentences. These are sentences that are built out of atomic sentences and one or more operators. We'll call the operators connectives in this version of our system. So if you hear me going back and forth between the word connective and operator, just know that I mean the same thing when I say each. So what we're going to do then is build on what we already know, and we're going to also extend our understanding of the notation that we can use to talk about atomic sentences. So let's get started. So it's true that there are loads and loads and loads of words out there, and there are loads and loads and loads of sentences out there, and it might feel a little bit overwhelming when you think about how you're supposed to take what look to be very complicated sentences in ordinary language and translate them into the notation of symbolic logic. Fortunately for us, we have a system of notation that captures the essential logical features that we need in order to do the work that is involved in chapters 3, 4, 6, and then later 7 and 8. All this work, in turn, forms part of the system that we'll be working on in chapters 9, 11, and 13. Okay, so as I mentioned, we've been looking at simple sentences. That is, sentences that involve a subject and a predicate in terms of the grammatical structure. In terms of logical structure, we're talking about named entities, that is, individual constants, and what we say about them, that is, predicates. So we'll take our individual constants and our predicates, and we will combine those with connectives so that we can generate more complicated sentences than we have been dealing with so far. So take a look at the sentences that are under the second bullet point. We have Flanny does not like any of the dogs. Al and Flanny are cats. Stu is in front of Al and Brett is in back of Flanny. Stu is not both in front of and in back of Flanny. It is not the case that either Flanny or Brett does not like Joe. Notice that, with the exception of the very first example, all of these sentences involve named entities and what we're saying about them. So, for example, Al is a cat, Flanny is a cat. So cat is predicated of, respectively, Al and Flanny. What we have in addition to our predicates and individual constants is a set of connectives. So look at the following words. In the first example, we have not. In the second example, we have and. In the third example, we have and. In the fourth example, we have not, and we have both and. And in the fourth example, we have not and either. Actually, two iterations of not. So if you take a look at the first example, the phrase any of the dogs is going to be phrasing that we will learn about in chapter 9. But I wanted to include it here just to give you a flavor of the ways in which, some of the ways in which we can complicate sentences. So we've got our individual constants. As I mentioned, we've got Flanny, we've got Al, we've got Stu, Brett, and Joe. And we have, out of the atomic sentences, built compound sentences by introducing connectives. And remember, the connectives in the examples are not, and either. All right, so we already know that atomic sentences are sentences that are either true or false. In other words, they are sentences that have a truth value. We know further that in Tarski's world, the truth or falsity of a sentence is determined by whether or not, expressed by the sentence, obtains in a world. In other words, is there a positive correspondence between the sentence and the given world? So we'd say the sentence, A is a dodeck, is true if and only if there is a dodeck named A in a given world. The way that we determine truth via our Boolean connectives, that is, by our connectives negation, conjunction, and disjunction, or in ordinary language, words like not, and or, is not simply a matter of comparing the sentence with the world. Instead, what we do is we take what are called possible truth values. So a sentence, A is a dodeck, is either true or false. Those are its possible truth values. We take a sentence's possible truth values and, combined with the meaning of a given connective, we generate a value for the sentence as a whole. So, for example, if we say Flanny and Al are cats, we will find out that there are 4 possible ways for this sentence to be true or false. Flanny is a cat is either true or false. Al is a cat is either true or false. But the sentence Flanny and Al are cats is going to be true or false based on the original truth values of the atomic sentences combined with the meaning of the connective and. And I can be even a little bit more technical here. Let's say we're not talking about the meaning of the connective and so much as we're talking about what are known as the truth definitions of the connective conjunction or the word and. So what we're saying here is that there are ways in which a conjunction sentence is true or false. And those are the same regardless of the circumstances of the individual sentences. More about that in a moment. But that's why we call these truth values truth definitions for a given connective. So before we move into what it means for a sentence that is governed by a negation or a conjunction or a disjunction to be true or false, let's talk about what our new notation is going to involve. So we're going to continue using the notation we already know, right? We're going to be using a predicate, the first letter of which is capitalized, and we'll be using in parentheticals lowercase letters for individual constants. Our connectives, negation, conjunction, and disjunction, will be symbolically notated by the operators hook, caret, and wedge. So here's how we will notate our sentences using negation, conjunction, and disjunction. Let's start with negation. What negation does is deny the sentence it's negating. So the ordinary language expressions will include language like not, it is false that, it is not the case that, and so forth. You've already seen the operator. Again, I'm going to use the language operator and connective to refer synonymously both to the symbol hook, but also to the name negation. So take a look at the examples. We have the hook in front of every sentence that's negated. It's not going to be the case that the hook comes behind or on the right side of the sentence that's negated. It always appears in front of or on the left side of the sentence that's negated. We can articulate the negation of an identity statement either, as you see in the example, the third example, It's not the case parenthetical, Al is identical with Flanny, close parenthetical. We also have in our notation toolbox the identity symbol with a cross through it. That slash tells us that it's not the case that X and Y are identical. How do we express whether or not sentences that are governed by a given connective are true or false? Well, we generate a truth table. And a truth table consists of possible truth values for any given sentence. We already said that any sentence in the universe, let's call it P, is either true or false. So when we say that the sentence P is negated, we're going to see how negation is defined by the original value as well as what we understand the function of negation to be. On the left-hand side of the vertical line is the set of possible values for the sentence P. And remember, P is just a stand-in for any sentence in the universe. P could be true or false. The definition of negation, then, is false when the sentence it's negating is true, and true when the sentence it's negating is false. The second of our third connectives is conjunction. Conjunction affirms the conjoining of two sentences. Typically, we see in ordinary language conjunction expressed by the words and, both, yet, still, moreover, nevertheless, and so forth. So when we have a conjunction sentence, we have a sentence that says X and Y are true, or we have a sentence that says both X and Y. Take a look at the examples below, and you'll see that the connective conjunction always appears between sentences, right? So it's not like the negation, which is always to the left of whatever sentence it negates. In other words, it's always out front, right? Conjunction is always sandwiched in between sentences. Here we have a truth table that shows us how we generate the possible truth values for a sentence governed by conjunction. Another way to put it is this: the values that you see in the column under the caret are the definitions for any sentence governed by conjunction. Notice also that there are 4 rows rather than, as with negation, 2 rows that reflect the definitions for conjunction. Why is that? Well, it's because rather than there being simply one sentence that's therefore either true or false, there are 2 sentences that are true or false, which means there are 4 possible permutations of truth values. Take a look at the column under the sentence P. There are 2 trues and 2 falses. Now take a look at the column under the sentence Q. The trues and falses alternate. Another way to think about this is by way of the following visual. Look at the row under look at the first row where P is true and Q is true. Now look at the second row where P is true and Q is false. The third row where P is false and Q is true. And the fourth row where both are false. These possible values exhaust the ways in which the truth values could appear for these 2 sentences. You could think about it in terms of something like the following. On Monday, it's true that I have pennies. It's also true I have quarters. On Tuesday, it's true I have pennies, but it's false I have quarters. On Wednesday, it's false I have pennies. It's true that I have quarters. And on Thursday, it's false that I have pennies, and it's false that I have quarters. In other words, it doesn't really matter what sentences you plug in. I hope it's clear now, if it wasn't before, that what we're talking about is the possible scenarios for these sentences in combination with each other. So, once we understand what these possible values are, we now look at the column under the conjunction symbol. The column under the conjunction symbol has the following values: true, false, false, false. So here's one way you can read how we determine the truth definitions for conjunction. True and true means the sentence as a whole, that is, the conjunction is true. True and false means the sentence as a whole, that is, conjunction is false. False and true, that is, the sentence as a whole, conjunction is false. And lastly, false and false means the sentence as a whole, that is, conjunction is false. Another way you might think about it is this. Ask yourself, is it true that I have both P and Q on row 1? Yes. It's true that I have P, it's true that I have Q, so it's both. So it's true that I have both. Is it true that I have both P and Q on row 2? No, it's false that I have both P and Q on row 2. That's because I don't have Q. In other words, it's false that I have Q. Is it true that I have both P and Q on row 3? It's not true that I have both P and Q on row 3. That's because it's false I have P. Lastly, is it true that I have both P and Q on row 4? It's not true that I have both P and Q on row 4. In other words, it's false that I have both P and Q on row 4. That's because it's false I have P and it's false I have Q. Here's another way to look at the setup of a truth table for not just conjunction, but for any sentence where there are 4 possible values of the constituent elements, that is, the sentences independently of the connective. So we have what are known as referent columns. Under P, half true, half false, and under Q, alternating true, false, true, false. So when you use the bool program, you'll have these referent columns. Lastly, let's look at the connective disjunction. The disjunction is the connective that expresses a disjunctive relationship between 2 sentences. Our ordinary language expressions for disjunction include or, either or, otherwise, and so forth. Now, there's going to be something a little bit apparently tricky about the or, but once you grasp what that apparent trickiness is, you'll see that, in fact, it's only apparent and it won't prevent you from understanding what's going on. But first, let's look at how this operator works in the notation. Like the conjunction, the disjunction is always sandwiched between sentences. The disjunction is never out in front of or behind a sentence or set of sentences. So you need 2 or more sentences if you're going to have a disjunction. Now we get to the apparent confusion about disjunction. If you think about how we ordinarily consider or use or, we typically think of it as exclusive. You can have soup or salad. The implication not stated is, but not both. But logic doesn't know from unstated implications, right? Instead, if you mean an exclusive or, you're going to have to assert it. Otherwise, the or is inclusive. I hope once we see a couple of examples, this will make some sense. So here's an example. If I have the sentence, Flanny or Shazi is black, that sentence is true provided at least one of those cats is black. So my cat Flanny is black. That sentence is true. We would say very comfortably that Since the sentence, Flanny is black, is true, the sentence, Flanny or Shazi is black, is true. All we need to know is that at least one of the disjuncts is true for the disjunction as a whole to be true. It could be the case that both Flanny and Shazi are black, and in fact, that is the case. I have a cat named Flanny, and she is black. Therefore, the sentence, Flanny or Shazi is black, is true. Turns out, my cat Shazi is also black, but that doesn't change the truth of the disjunction. Let's see how this plays out in the truth table. Once again, we have our possible values. P is true, Q is true. P is true, Q is false. That's respectively rows 1 and 2. Row 3, P is false, Q is true. And row 4, each of the sentences P and Q are false. When we take those initial values and we understand the function of the or, we end up with or being true in 3 out of 4 cases. In other words, the or is false when and only when each of the disjuncts, is false. Just like and, or the conjunction, is true when and only when each of the conjuncts is true. So provided that at least one of the disjuncts is true, the sentence as a whole, that is the disjunction, is true. It's false when and only when each of the disjuncts is false. So let's try the previous example in terms of the sentences, I have pennies, I have quarters, and bring them to bear here. If it's true that I have pennies, then it's true that I have pennies or quarters. If it's true that I have pennies, then it's true I have pennies or quarters. If it's false that I have pennies, but it's true I have quarters, then it's true I have one or the other. And then lastly, if it's false I have pennies, and if it's false I have quarters, then it's false that I have one or the other. Okay, so far what we've accomplished is this. We have introduced our new notation, that is notation that will allow us to translate ordinary language sentences into compound sentences that include one or more of our 3 connectives, negation, conjunction, and disjunction. We also understand in a rudimentary way where and how we place our operators when we're translating. So for example, we know that the negation always goes to the left of whatever sentence is being negated. We also know that the conjunction and the disjunction are sandwiched in between sentences. In other words, there are always sentences on either side of these connectives. Now what we want to do is take a look at how parentheses work in a compound sentence. So what we use parentheses for here is to denote or set off compound sentences as a unit. So take a look, for example, at the sentence under the the 2 sentences under the first bullet point. In each, there are 2 connectives. So we have the operator hook and the operator caret in the first sentence, and then in the second sentence, we have the wedge and the hook. In other words, we have a negation and conjunction, respectively, in the first sentence, and a disjunction and negation, respectively, in the second. Notice that the negation scope in the first sentence is tet A. Negation's scope in the second sentence is medium A. On the other hand, the scope of the conjunction in the first sentence and the disjunction in the second sentence is the sentence as a whole. In other words, both sides of the conjunction and both sides of the disjunction are covered, if you will, by each of those connectives. But take a look now at the second bullet point, more specifically the examples underneath that second bullet point. Notice that when you have a set of parentheses around, in this case, the conjunction, we should read that sentence as being a unit, a single entity, if you will. The negation out front of the parentheses tells us that the statement as a whole, that is, the conjunction, is being negated. So it's not both. As opposed to in the first example under the first bullet point, the negation covers only tet A. So the scope is different. In the first case, the scope is limited to the sentence A is a tet. In the second instance, under the second bullet, or sorry, the first instance under the second bullet point, or the second instance that I'm talking about, the negation covers the conjunction. So whatever the conjunction says, the negation rejects it. Now let's take a look at the second example under the second bullet point. Notice that the disjunction is bound by a set of parentheses. So the sentence, either C is a dodeck or A is medium, acts as a unit. That means then that the sentence, that means then that the conjunction governs the sentence as a whole. The sentence says, A is a tet and either one of these two things is the case. One of the ways you might think about the parentheses is as follows. Whatever is inside the parentheses is never going to be the main connective. It's never going to be the governing operator. It's never going to drive the sentence. Notice how from example 2 to example 3 under the second bullet point, the parentheses are changed so that we get the following reading in the third example. Either A is a tet and C is a dodeck, or A is medium. In the second example under the second bullet point, remember we have A is a tet and either C is a dodeck or A is medium. So the reading changes depending on where the parentheses are. That should give you a pretty good idea of how parentheses function. There are, of course, more complicated sentences, but the point of this video is to get us started, right? To give us the sort of the most rudimentary ideas that will allow us to make sense of more complicated sentences. So lastly, let's just summarize what we know given what we've covered so far. The connective negation, symbolized by a hook, is always written to the left of whatever sentence it negates. Conjunction and disjunction, that is caret and wedge, are always sandwiched between sentences. They're like the hinges that connect a door to a wall. That notion of hinges is going to be, at least I hope, useful when we look at rules for assembling and disassembling sentences. That will happen beginning in chapter 6. In addition, parentheses always go around complete sentences that are to be treated as a single unit. Don't forget that the order and capitalization of predicates and the lowercase of individual constants remains as it was from the beginning, that is from chapter 1. And also from chapter 1, remember that when you have two or more individual constants, the order is important. A correct translation, lastly, will have the same truth conditions in first-order logic as it does in English. To have the same truth conditions means they have the same truth values in all possible circumstances. We understand what those truth definitions are for negation, conjunction, and disjunction. Remember that the definition of negation is the opposite truth value of whatever sentence is negated. The definition of conjunction is such that a conjunction is true when, and only when, each of the conjuncts is true. Lastly, the definition of disjunction is such that a disjunction is false when and only when each of the disjuncts is false. Now that we know that negation, conjunction, and disjunction are each connectives whose truth definitions are functions of the atomic sentences and the meaning of the respective connective in each sentence, we can start to see how sentences could be equivalent to each other. One of the things that we'll want to do is learn how to use Boole to construct a truth table. But right now, let's just focus on the following. Let's focus on what it is that we're saying when we say that sentences are tautologically, aka truth functionally, equivalent to each other. So we'll get into what it means to build a truth table in a little bit. Okay, so what I'm going to do is I'm going to take us to Boole, and I'll take us to Boole where you will see that I have already laid out the atomic sentences for the double negation equivalence and the two DeMorgan's equivalences. And then what I'd like us to do, like I said a moment ago, is to focus on understanding how it is that the sentences in question are truth functionally equivalent. Okay, so let's take a look at the Boole program. This is the older version of Boole, but the functionality is the same as the newer one. On the left side of this thick set of vertical lines is the reference column. So this tells us what our atomic sentence values are. We know from our discussion of truth values that any sentence in the universe is either true or false. So here is P, a representative of any sentence in the universe. It's either true or false. Now take a look at the right side of the vertical line and you see two sentences, P and not P. Now the first sentence, P, is not negated. There's no conjunction in between it and a second sentence. There's no disjunction between it and a second sentence. So since there's no value to calculate or determine, we simply input the original values. And notice, by the way, that when you put your cursor in the column under the atomic sentence P, your reference column highlights or is highlighted. So that tells you to just duplicate those values. Now let's move over to our second sentence. And when we click in the column under the first negation, that is the negation to the immediate left of the sentence P, we're told that we should determine the values by reference to the original sentence P. So why are we determining the values of the negation to the immediate left of P rather than the second negation over? Or another way of putting it is, why aren't we calculating the values of the far left negation? Well, that's because, remember, the far left negation is the negation that governs or controls, if you will, the values of the sentence as a whole. And that means that its values are the result of, are the functions of, the original value P that is then negated. So if P is true, not P is false. If P is false, not P is true. Now we're in a position to generate our values for the sentence not P, and we get not false coming out true and not true coming out false. Now, for the sake of visual clarity, I'm going to erase the values under not P and look at what you get. In the column under the main connective, the values of not P are identical to the sentence P. So these two sentences, P and not P, are truth functionally equivalent. Okay, let's move on to another sentence. This is the sentence of a pair of what are known as DeMorgan's equivalences. Now remember what you learned originally in terms of the not just the truth definitions, but the notion of a main or governing operator or connective. When you have two or more connectives, only one is the main connective. I had mentioned earlier that the connective in a parenthetical is never going to be the main connective. If there is no set of parentheses, then the main connective is determined by its scope. Notice that in sentence 2, the scope of the first negation is simply the sentence P. The second negation is simply the sentence Q, while the disjunction brings not P together with not Q. So we're going to respectively determine the conjunction values first, then each of the negations in terms of the sub-connectives. So what do we know about a conjunction? Its definitions are as follows. The conjunction is true when and only when each of the conjuncts is true. Look at the reference columns. Otherwise, the sentence is false. What do we know about the truth definition of negation? The negation's value is always the opposite value of the sentence negated. Hence, not true is false, not false is true, and so on down the line. Now let's move over to our second sentence. Notice if I click in the column under the main connective, I'm told that its values are determined by each of the negations. So we have to, again, just as a reminder, determine those values first. When I click in the column under the negation, my referent column is clear. Not true is false. Not true is false. Not false is true. Not false is true. Move over to the second negation. Not true is false. Not false is true. Not true is false. Not false is true. Now I'm in a position to determine the values of disjunction. We know that the disjunction is defined as follows. A disjunction is false when and only when each of the disjuncts is false. In all other cases, it's true. So notice we have negation P, false, negation Q, false. So negation P or negation Q is false. In all other instances, at least one of the disjuncts is true, so the disjunction as a whole is true. Now, what are we looking at to compare the sentences in terms of truth functional or tautological equivalence? Column 1, column 2. Column 1 is the values under the negation. Column 2 is the values under the disjunction. And just so that it's easy for you to see what we're comparing, I'm going to eliminate the sub-values. Okay, take a look. Row 1, the values are identical. Row 2, row 3, row 4, the values are all identical. We can see then that these two sentences are truth functionally equivalent. That means that whenever you say not both, you're saying either not one or not the other. Similarly, or the same, when you say either not one or not the other, you're saying not both. All right, let's look at our last DeMorgan's equivalences. Once again, we have a negation, this time covering a disjunction, and then we have two negations, one on each side of a conjunction. Let's just compare that real quick with the first DeMorgan's equivalence that we looked at. There, the negation covered a disjunction. There, the negation covered a conjunction. Here, the negation covers a disjunction. In the first DeMorgan's equivalence, we had a negation on either side of a disjunction. Here, it's on either side of a conjunction. How do we read each sentence? We can read them as follows. Not either or neither. So neither one. The second sentence says, both are not, or not this one and not that one. Let's determine the values. Our suboperator, our subconnective, is the disjunction. We know that a disjunction is false when and only when each of the disjuncts is false. So our values are true, 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 false. Now we negate those values to get the value of the sentence as a whole. False, 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 true. Now we're ready to move on to sentence 2. We have false, false, true, true. False, true, false, true. We know that a conjunction is false, rephrase, a conjunction is true when and only when each of the conjuncts is true. So we have the following: false, 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 true. Now remember what we're comparing. We're comparing the values under the conjunction with the values under the disjunction. For the sake of visual clarity, let me go ahead and eliminate the subvalues. Once we've calculated or determined the values of the sentence as a whole, in this case the conjunction, and in this case the negation, we don't need those subvalues. They're the elements that inform the values of the whole. Notice that in each row, the values are identical. So the sentence not both, the sentence not either is equivalent to both are not, and vice versa. I hope this brief tutorial helps you get started on Chapter 3, Boolean connectives, in Barwise, Etchemendy, and Barker-Plummer's Language, Truth, and Logic.